at this time. Okay, so let's take a look at the following question and let's work through another limiting reactant product together. So we have magnesium metal reacts with aluminum chloride to yield magnesium chloride and aluminum metal. So let's start off. So the formula for magnesium is just Mg solid. Now in the chat, aluminum chloride, let's break apart aluminum chloride and let's determine the formula of aluminum chloride. So what would the formula be for aluminum chloride? And don't be shy to type in chat at this time or unmute and state your answer. Yep. Yeah, so for Zoom, there have been some technical issues associated with joining Zoom meetings from Canvas. That's why I have all these meetings recorded as a backup as well. So for aluminum chloride, it's AlCl3 solid. So the way that we got that is aluminum has a charge of 3+, chloride has a charge of -1. If we cross our charges, we get AlCl3. Likewise, would someone like to type in the chat, what would the formula be for magnesium chloride? What would the formula be for magnesium chloride? So this is a review of our nomenclature. It's a critical skill that we need to maintain and develop. Yep, MgCl2, that's exactly right. Magnesium as a 2A metal has a charge of +2. Chloride has a charge of -1. We cross our charges and that gives us MgCl2. As a byproduct, we also get aluminum metal. Now, let's think really carefully about this. Is this equation balanced? So is this equation balanced as written? Do we have the same number of atoms of each element on each side? Is this equation balanced? No. Now, remember when we talked about equations where we have different numbers of an ion on each side? What method can we use to figure out our coefficient? What method did we use last time when we have an ion on both sides of our chemical equation with different numbers of that ion? So just as a refresher, we can use the least common multiple method. So if we have 3 chlorines on the left and 2 chlorines on the right, yep, the least common multiple method. So then, what's the least common multiple of 3 and 2? What's the smallest common multiple? What's the smallest common multiple? 6, exactly right. So then, we're going to plug in a coefficient of 2 for aluminum chloride and a coefficient of 3 for magnesium chloride. From there, we balance magnesium and aluminum, and our equation is now completely balanced. Okay, so now that we have our balanced equation, we can actually do some stoichiometry here. So we're asked to calculate the mass of magnesium chloride when 2.5 moles of magnesium and 2 moles of aluminum chloride are mixed. Okay, so let's think really carefully about the following problem. My question to all of you is, do we know if there's a limiting reactant at play? Can we assume that our reagents are in equal quantities? Do we know if our reagents are in stoichiometric amounts? Or do we have to look for a limiting reactant in this case? Do we think, yeah, so we're going to start by always checking for a limiting reactant. The problem will not tell you this is a limiting reactant problem, but you should always be on the lookout for limiting reactants to pop up. Okay, so we're going to apply the product method. We're going to apply the product method. So first things first, we have 2.5 moles of magnesium, and we're going to convert our moles of magnesium to moles of magnesium chloride and then to grams of magnesium chloride. Okay, So now that we have our marching orders, now that we have our unit conversion map, if we're going from moles of magnesium to moles of magnesium chloride, how many moles of magnesium chloride do we have per mole of magnesium? What's our mole to mole ratio? What's our ratio of coefficients? Yep, 3 to 3, exactly right. We have 3 moles of magnesium chloride per every 3 moles of magnesium. And then finally, to calculate the grams of magnesium chloride, we need to know the grams of magnesium chloride per mole of magnesium chloride. And would someone like to really quickly on their calculator figure out and tell me the molar mass of magnesium chloride? Could someone please quickly calculate that and tell that to me? Or type that in the chat. What is the molar mass of magnesium chloride? Yep, about 94.9, exactly right. Okay, perfect. So we have a mass of 24 gram per mole for magnesium plus 35.5 gram per mole for chlorine, and we have 2 chlorine atoms, and that gives us 94.9 gram per mole of magnesium chloride. Perfect. So now we're going to punch this in to our calculator, and we're going to figure out, so this is from magnesium, how many grams of magnesium chloride do we get? So we're going to take 2.5 times 94.9, and that gives us 237.2 grams, which we then round to 240 grams of magnesium chloride. But we aren't done in this problem. This is just our first calculation. We're going to need to also calculate the mass of magnesium chloride generated from our second reactant. Okay, so let's repeat this process for our second reactant. So considering we have 2 moles of aluminum chloride, we're going to do the same conversion, except this time we're going to need to convert moles of aluminum chloride to moles of magnesium chloride. And my question to all of you is, looking at our equation, how many moles of aluminum chloride are reacting in this balanced chemical equation? What is our coefficient for aluminum chloride? 2. Yep. So we have 3 moles of magnesium chloride per 2 moles of aluminum chloride. Finally, we have 94.9 grams of magnesium chloride per mole of magnesium chloride. And if we punch that into our calculator, we get a total of 284.7 grams, which we round to 280 grams of magnesium chloride. And this is from our aluminum chloride. So my question to all of you is, which of these 2 reactants is limiting, magnesium or aluminum chloride? Which reactant produces the least amount of product? Which reactant produces the least amount of product, magnesium or aluminum chloride? Which of these mass values is smaller? I see a lot of people typing magnesium. That's exactly right. So we have magnesium as limiting. Perfect. Does that make sense to everyone? Does this product method seem okay to everyone? Is everyone comfortable with this so far? Okay. So let's keep going now, and let's talk about another method called the Icy Ii method. This method is really useful because the skills developed in this Icy Ii method will be used again when you're in 102 to handle equilibrium problems. So that's why we're teaching the ICE method. So first things first, we need to calculate the moles of each reactant. We're going to figure out the moles. You're going to put the moles of each reactant in your initial row in the ICE table. Okay? Now, the reaction will proceed and consume, quote unquote, X. So it will consume X moles of reactant and produce a multiple of X moles of product. And the exact multiple of X is based on the chemical equation reaction coefficient. So depending on your coefficients, you'll consume different amounts of reactant and produce different amounts of product. Okay, so what you're going to do is you're going to place the reaction coefficient for your reactant times X in the change row for each reactant. So for example, if we had 2H2O2 decomposing, we'd write this as minus 2X because our coefficient is 2 and this is a reactant. Okay? Now, a really important idea, the final moles of reactant should be 0 if the reaction went to completion. If we used up all of our reactant, if the reactant is limiting, we should have none of our reactant remaining at the end of this reaction. Okay. So what you're going to do is you're going to add together the initial and change columns of the ICE table for each reactant and product to give an expression for the final moles of each reactant and product. Now, because one reactant will be completely consumed, you're going to set the final moles equal to 0 for each reactant. So your initial plus change is equal to 0. In other words, your initial minus some number, some coefficient times X is going to be equal to 0. And what you're going to do is you're going to solve for X. Now, a nice shortcut, and this is how I'm able to figure out limiting reactants so quickly, if you divide the initial moles of each reactant by the reaction coefficient, that will give you X. So X is the initial moles divided by the reaction coefficient. And the key feature of this method, the smaller value of X is the limiting reactant. Now, once you've solved for X, for example, X is equal to 0.5, you're going to substitute X for the final moles expressions for each reactant and product. Now, this is the mechanics behind the ICE table, and it may be a little hard to grasp just from this step-by-step procedure. So let's apply this step-by-step procedure to the following problem. Okay, so let's try to address the following problem. So first things first, I'm going to write my reactants. So we have H2S and iron 3 chloride. So I'm going to write my reactants and I'm going to write my products. Okay, so we've written our reactants and products. Now we need to calculate our initial moles. Okay? So we have 64.0 grams of H2S. Can we convert this grams of H2S? Can we go from grams of H2S to moles of H2S? Can we go from grams to moles? Are we comfortable doing that? Yeah. So then we know in 1 mole of H2S, we know that there are 34.0 grams. So all we have to do is punch that into the calculator. And so for our initial moles of H2S, we get 1.88235. We're going to carry as many digits as possible. I'm just carrying to 5 decimal places because that's what fits in this column. Okay, we're going to repeat the same calculation, and we're going to calculate the initial moles of iron 3 chloride. So we have 180.0 grams, and we know that in 1 mole of iron 3 chloride, we have, would someone like to tell me, would someone like to provide me the molar mass of iron 3 chloride? In 1 mole of iron 3 chloride, we have how many grams? Could we calculate that? I'm mainly making the point that you're to retain as many sig figs as possible because we don't want to truncate sig figs towards the end. The reason why I stopped there is that's the maximum I can write in this box. But you want to retain as many sig figs as possible in your calculator so that way you don't introduce rounding errors. Does that make sense? You want to retain as many digits as possible. So, has anyone finished calculating the molar mass of iron 3 chloride? Would someone like to provide that for the class? What's the molar mass of iron 3 chloride? This is you always want to make sure you can calculate your molar masses efficiently. Has anyone finished calculating the molar mass? Yep, exactly right, 162.3. Okay, so now we punch that into our calculator. And that gives us 1.10905 moles. Okay, now at the start of our reaction, and let's think about this really carefully. At the start of our reaction, will there be any moles of product? Are we starting with any moles of product? Have I given you any mass or moles of product at the start of our reaction? Would there be any product if our reaction hasn't started yet? Will we have any product if our reaction has not started yet? No, exactly right, exactly right. So we're going to put a 0 for the initial moles of product. Okay, now we're going to write the change coefficients. And so I'm going to write my coefficients just so that way it's easy for us to see what's going on here. So what would the change coefficient be for H2S? So we have some number x times our reaction coefficient. So instead of minus x, what's our reaction coefficient for H2S? What's our reaction coefficient? What is the number in front of H2S? 3. So it would be minus 3x. Okay. What would the change expression be for iron 3 chloride? Instead of minus 3x, it would be minus, what would the change expression be for iron 3 chloride? Yep, it would be minus 2x. Okay, now you may ask, why is it minus? We are using up our reactant. We are consuming our reactant to generate product. So then, if we're making product, would the change coefficient be negative or positive for our product? For our product, positive, exactly right. So it would be plus X for iron 3 sulfide. And what would it be for hydrochloric acid? Would it be plus 1, plus 2? It would be plus 6X, exactly right. Okay. So now what we're going to do is we're going to write out each of our change expressions. We're going to write out each of our change expressions. So for H2S, we have 1.88235 minus 3x is equal to 0. As our shortcut, our x is equal to 1.88235 over 3. And if we punch that into our calculator, we in turn get a value of x of 0.62745. Okay? So this is essentially describing the amount of reaction progress necessary to completely consume all of our H2S. We're going to do the same calculation for iron 3 chloride. So we have 1.10905 moles minus 2x is equal to 0. We set these equal to 0 because one of our reactants is limiting. And when we completely use up one of our reactants, we will have none of it remaining. And the reactant with the smaller value of x that takes the least amount of reaction progress to be completely consumed is limiting. So solving for x, we have 1.10905 over 2. And that in turn gives us a value of x of 0.5545. Now, I'd like you, given this information, I'd like you to tell me which of these values of x is smaller and which of our reactants is limiting. Which of our reactants is limiting? H2S, hydrogen sulfide, or iron 3 chloride? Which reactant is limiting? Yep, exactly right. Our iron 3 chloride is limiting. Why? It has the smaller value of x. So now what we're going to do is we're going to plug in this value of x. So we're going to have 3 times 0.5545 and then okay. So let me write that here, minus 3 times 0.5. One moment. Allow me one moment to reopen OneNote. Give me 1 second to do that. Sometimes it freezes up. Sorry for that interruption. Yep, so we've identified our iron 3 chloride as limiting, and now we're going to plug in this value of x in all of our expressions. So we'd have 3 times 0.5545 for our change expression. For iron 3 chloride, we have 2 times 0.5545, and we're going to end up with 0 moles of iron 3 chloride in the end because it is limiting. For our iron 3 sulfide, we're going to have plus 0.5545 moles. And for hydrochloric acid, we're going to have plus 6 times 0.5545. We've essentially plugged in the value of x for our limiting reactant into each of our change expressions. Does that make sense so far? Any questions so far? So now all we have to do is punch this into our calculator. So let's do this first expression here. So we're going to take 1.88235 minus 3 times 0.5545. And at the end, from our first change expression, we'll get 0.21885 moles left over. For our product, we'll make 0.5545 moles of iron 3 sulfide. And for hydrochloric acid, we have 6 times 0.5545, which gives us 3.327 moles of hydrochloric acid produced. So the really wonderful thing about NICE table is that it allows you to very quickly calculate the amount of each reactant remaining and each product generated very efficiently. Does the logic behind the ICE table make sense? Are there any questions on the ICE table? Any questions so far? So then, reading our original question, we're asked how many grams of iron 3 sulfide can form. So all we have to do to complete this problem, is to take our moles. So we have 0.5545 moles of Fe2S3. And to calculate the grams, all we need to do is multiply by our molar mass. So we have 56 times 2 plus 32 times 3. And we multiply by our molar mass, which is 208 grams of Fe2S3 per 1 mole of iron 3 sulfide. And if we punch that into our calculator, we get, in the end, 115 grams of iron 3 sulfide. And the reason why we report 3 sig figs is if we go all the way to our start of our problem, how many sig figs do we start out with? How many sig figs are we starting off with? How many sig figs are we starting off with? 3, exactly right. So we report up to 3 sig figs. Does that make sense to everyone? Does the logic behind the ICE table make sense so far? Oops, let's zoom down. Any questions before I let you loose on your own problem? Since I don't see any other questions, let's now work on our own problem. So I'd like you to tell me, given the following balanced equation, I'd like you to calculate how many grams of nitrogen monoxide can form when 30 grams of ammonia and 40 grams of oxygen react. And remember, what I want you to start with is you need to calculate the moles. So you should calculate the moles of each reactant and product at the start, write your change coefficients, solve for X, and determine which of the reactants is limiting, which of the reactants has a smaller value of X. So what I'm going to do is I'm going to let you loose on this problem for about 5 minutes, and then we'll come together as a group to discuss in about 5 minutes. And don't be shy to ask your questions in the chat during this problem-solving period. Oops, one moment. Let me zoom in so that way we can get a good view. Okay, perfect. So you're welcome to start on this problem, and if you have any questions, don't be shy to ask at this time. And we'll come together to discuss at 1:42. Any questions during this time? And don't be shy to message me your answer for the grams of nitrogen monoxide as a private message, or message me your answer for any of these steps as a private message, and I'd be more than willing to check your work and provide feedback. This is really your opportunity to work through the problem, and if you have any questions as you're solving the problem, I'm more than available to help you address those questions. If not, we'll be resuming for our group discussion in about 2 minutes. But I really do want to see some messages with proposed answers in the chat, just so that way I know that everyone's comfortable with this concept. And if there are any concept or portions of this method that you'd like me to cover in more detail, don't be shy to ask. Okay, so let's come together to discuss this problem, and I'm going to need your help in solving and working through this problem. So first and foremost, we're going to calculate our moles. So for our ammonia, so let's write each of our reactants. So we have ammonia and oxygen reacting to yield nitrogen monoxide and water. Wonderful. We have 30.0 grams of ammonia. And in 1 mole of ammonia, we have 17.0 grams. So that gives us, for our moles of ammonia, we have 30 divided by 17. That gives us 1.7647 moles of ammonia. So we're going to put that into our initial moles column. My question to all of you is, if you've been doing your mole calculations, how many moles of oxygen do we have? How many moles of oxygen do we have? Would someone be willing to type that in the chat? How many moles of oxygen do we have initially? How many moles of oxygen do we have? If we've been attempting these calculations, how many moles of oxygen would we have? Yep, roughly 1.25. Yep, so if we take 40 over 32, we get 1.25 moles of oxygen. Okay, we're now going to fill in for our products. We have 0 initial moles of product. And now we're going to fill in our reaction coefficients from our chemical equation. We have a 4 in front of ammonia, a 5 in front of O2, a 4 in front of nitrogen monoxide, and a 6 in front of water. Oh, Fabiola, when you're calculating the moles of oxygen, so the number that you calculated is the moles of atomic oxygen. Since we're trying to figure out the moles of our reactant, which is molecular oxygen, we need to use the molar mass of O2. But that's a common point. Whenever we refer to the name of an element, we're often referring to the molecular form if it's reacting in a chemical equation. Does that make sense? Perfect. Okay, so in terms of our change coefficients, let's start with ammonia. So what would our change coefficient be? I want the sign and the number. So what times x? So what would the change coefficient be for ammonia? If its reaction coefficient is 4, what's our change coefficient going to be? And don't be shy to type it in the chat. Yep, minus 4x. Exactly right. It's minus because we consume reactants to generate products. Okay, what would the change coefficient be for O2? What would the change coefficient be for oxygen? Yep, minus 5x. Exactly right. Nitrogen monoxide would be plus 4x. And what would the change coefficient be for water? What would it be for water? Yep, plus 6x. Wonderful, wonderful. So we have everything established now. And what we're going to do is for each of our reactants, we're going to calculate the value of x. And remember our shortcut. You can simply take your initial moles. So for ammonia, you take the initial moles and you divide it by your reaction coefficient. This is such a nice trick because it saves you just so much time. So we'll take 1.7647 and divide it by 4, and we get 0.44117. Let's do the exact same process for oxygen. And would someone like to tell me what is the change, what is the reaction progress? What is the value of x for oxygen if we take 1.25 and divide it by 5? Yep, 0.25. That's exactly right. Okay, perfect. So then my question to all of you is, looking at these values of x, which reactant is limiting? Which reactant is limiting? O2. Yep, exactly right. Because it has the smaller value of x. So we're going to plug in this value of x into all of our change expressions. Okay, so we're going to have minus 4 times 0.25 minus 5 times 0.25 plus 4 times 0.25 and then plus 6 times 0.25. Now the real beauty of the ICE table and the real reason why we use the ICE table is because it gives us the amounts of each species, reactants and products at the end of our reaction. So in this case, we're asked to calculate the grams of nitrogen monoxide. So we're going to need to use our ICE table to figure out the final moles. Now, let's just do that really quickly. So for our final moles for ammonia, we'd have 0.7647. For oxygen, we'd have 0 moles because oxygen is limiting. For nitrogen monoxide, we have 1.0 moles. Oh, 1.00, since technically this should have 3 sig figs. And for water, we'd have 0.25 times 6, which gives us 1.50 moles. Okay, wonderful. So now that we have our moles of nitrogen monoxide, we'll plug in 1.0 moles of nitrogen monoxide times the molar mass of nitrogen monoxide, which is 30.0 gram per mole of nitrogen monoxide, and that gives us 30.0 grams of nitrogen monoxide. So if we take 1.7647 minus this number here, we get 0.7647. And you can try punching that into your calculator at this time. Essentially what you're doing is you're adding together your initial and your change column, and that gives you the final. Does that make sense? Perfect. So now that we've calculated the expected mass of product, and one question that I really want to drive home to you, could we solve this problem using the product method? Could we solve this problem using the product method? Can we just as easily use the product method? Is there anything special about the ICE table? No, not really. But where the ICE table is most useful is when you need to report the amount of every single species in solution. And believe me, if you're doing this for every single species, the ICE table is faster than the product method. But if you just need to know the mass of a certain product, such as nitrogen monoxide in this case, you're honestly better off using the product method. These are all just tools and frameworks for you to use, and whatever you feel comfortable with using, that's what I would stick with. Is everyone comfortable with this example? Does the ICE method make sense to everyone? Any questions on the ICE method? We'll be doing a little bit more practice just to make sure we're comfortable. And you will see these kinds of tables again in 102. So that's why I'm showing you the ICE method for limiting reactants, because this framework, yes, in general, the ICE method is more applicable to all types of problems. It is very general in scope, but it's a little slower. That's the trade-off. But it certainly keeps your calculations organized, and that's what I love about it. It's very organized, very clear. If any mistakes are made, they're very easy to check and correct. Not in this case. We have calculated the excess amount of ammonia. We know how many moles of excess ammonia, and we can calculate it, but we're not required to in this problem. So we will see an example where we have to calculate the excess. So this is just a repeat page in case you need more space to do work. What I want you to do now is, given both of these methods that I've showed you, I'm going to give you the following word expression, and I'd like you to calculate the mass of product generated and the mass of excess reactant. This is exactly the way that you'd see problems on the exam. So you'd need to be able to write a balanced equation, and then at the end of writing your balanced equation, perform stoichiometry to identify the limiting reactant, calculate the mass of product, and then tell me how much excess reactant is left over. Now, in order to ensure that we have a productive session, we're going to work and we're going to together generate our chemical equation. But I'm going to make everyone in the chat do some heavy lifting here. So for sodium bromide, would someone like to tell me what is the formula of sodium bromide? What is the formula of sodium bromide? NaBr, exactly right. So we have NaBr. Let's write this a little bit higher up. So we have NaBr. Okay, and would someone like to volunteer the formula for silver nitrate? Again, nomenclature is an invaluable skill. So would someone like to tell me? Yep, AgNO3. Okay. Would someone else in the chat like to volunteer the formula for silver bromide? Just so that way we have a nice class consensus. Would someone like to volunteer the formula for silver bromide? Thank you. Perfect. The answers in the chat are spot on. So we're making AgBr. And for sodium nitrate, would someone like to tell me, just to finish this off, what's the formula for sodium nitrate? Yep, NaNO3. Okay, wonderful. Now, before we break off into groups and before we go to identify our limiting and excess reactant, would someone like to tell me right away, is this equation balanced? Is this equation balanced? Should I put a check mark? Should I put a check mark here? For those who say it's not balanced, which element is not balanced? Just to check. So looking at sodium, we have one sodium atom each on each side. For bromine, we have one bromine atom. For silver, we have one each. For nitrogen, we have one each. And for oxygen, we have three each. So yes, this equation is balanced. But it's always good to check, always good to check. Now that we have our balanced chemical equation, I'd like you to take these initial masses of each reactant, and I'd like you to tell me the mass of silver bromide generated. So I'd like you to calculate that at this time. And we'll resume our discussion in about 4 minutes at 2 o'clock. And don't be shy to send me your responses for part 1 and 2 via a private message, or you can type it into our general chat. I want to be able to provide feedback, and I want to make sure you have practice on exam level questions. Any questions so far? How's everyone going along with working through this problem? You can use any method, the product method or the ICE method. Okay, so we're going to come together to discuss this problem now. You want to make sure that you're able to work through these kinds of stoichiometry problems efficiently. So in terms of, since we only have to calculate the mass of product and the mass of one excess reactant, I'm going to choose to use the product method. Okay, so first things first, I'm going to need to calculate the moles of each of my reactants. So I have 50 grams of sodium bromide. And I know in 1 mole of sodium bromide, I have how many grams? So for sodium, we have 22.98 plus bromine, which is 79.9. And that gives us a molar mass for sodium bromide. Let's calculate that really quickly. Of about 102.9 gram per mole. So let's plug that in. Okay. Now we're going from grams of sodium bromide to grams of silver bromide. So my question to all of you is how many moles of silver bromide, let's write that a little more clearly, how many moles of silver bromide, oops, one moment. So my question to all of you is, how many moles of silver bromide do we make per mole of sodium bromide consumed? What is our mole to mole ratio? 1 to 1, exactly right. And it's good to see all that participation in the chat. It's wonderful. Okay, finally, how many grams of silver bromide are present in 1 mole of silver bromide? So let's calculate that. So we have 107 for silver plus 79.9 for bromine, and that gives us 186.9. Let's just check that really quickly in our periodic table. Okay, perfect. Okay, wonderful. So now all we have to do is punch this entire expression in our calculator, and we're calculating from our sodium bromide, how many grams of silver bromide do we produce? So let's enter that into our calculator just line by line. So we have 50 over 102.9 times 1 times 186.9. And that in turn gives us 90.81 grams of silver bromide that we round to 91 grams of silver bromide. Are we done? Can we just say we made 91 grams of silver bromide and call it a day? Would that be a complete answer? No. We haven't checked to see if silver nitrate is limiting. So starting off, we have 100 grams of silver nitrate. And we know that in 1 mole of silver nitrate, we have how many grams? Well, we can calculate that. We always have the tools to calculate things. So we have 107 grams for silver, 14 grams for nitrogen, and 16 grams times 3 for oxygen. And that in turn gives us a mass of 169 gram per mole. My next question is, how many moles of silver bromide do we make per mole of silver nitrate? What is our mole to mole ratio? What is our mole to mole ratio? 1 to 1, exactly right. Now, I always like to write out my conversions in a one line because it's very easy to read, very easy to check my work, and I don't have to hassle with figuring out where this random number came from. So, continuing on, we have 186.9 grams of silver bromide per 1 mole of silver bromide. That we just got from up here. Molar mass is the same for the same product, right? So now all we have to do is enter this entire one-line expression into our calculator. So from our silver nitrate, we would see we have how many grams of silver bromide produced. So let's punch that into our calculator. And would someone like to propose an answer for this line calculation before I finish punching it into my calculator? So how many grams of silver bromide? Yep, I see a lot of people writing 110.5 grams that we then round to 110 grams of silver bromide. Actually, we'd round it to 111 because this number has technically 3 sig figs with the dot at the end. Okay, now let's compare. Which of my two reactants are limiting? Which reactant makes the least amount of product? Sodium bromide or silver nitrate? Sodium bromide, exactly right. So sodium bromide is limiting. So in reality, we only make 91 grams of silver bromide. Perfect, perfect. Now, as one follow-up, as a follow-up to this entire problem, we know that we have 100 grams of silver nitrate, right? And to calculate our excess reactant remaining, we take our 100 grams of silver nitrate, we subtract our 91 grams of silver bromide, and all we have to do is convert the grams of product, silver bromide, to the grams of silver nitrate. And we know how to do that. We're essentially doing this conversion that we did up here in reverse. So we know that in 1 mole of silver bromide, we have 186.9 grams. We also know that we have 1 mole of silver nitrate per 1 mole of silver bromide. Okay, now to finish off this conversion, sorry about that, the page quickly swapped. To finish off this conversion, all we have to do now is convert to the grams of silver nitrate. So we have 169 grams per 1 mole of silver nitrate. So punching this into our calculator really quickly, would someone like to volunteer in the chat what mass of excess reactant, what mass of silver nitrate do we have remaining? What mass of excess reactant do we have remaining? How much silver nitrate do we have left over at the end of this reaction? So let's punch this expression into our calculators. And if I'd like someone to volunteer and tell me how much excess reactant we have left over at the end of our reaction. So let's take a moment and let's make sure we're comfortable entering these values into our calculator. So in effect, we're taking the mass of excess reactant and converting the grams of product to the grams of reactant consumed. And I hear 17.7, that's exactly right. So we have 17.7 grams of silver nitrate remaining. Perfect. Any questions on this example? If not, let's try another problem. Let's keep doing some examples just to reinforce this concept. Okay, so let's work on and let's do an example of a relatively complicated exam problem. So this will be the last problem that we'll be working on today for this session. So let's consider a reaction between calcium hydroxide and hydrochloric acid to form aqueous calcium chloride and water. So we're given that if we combine 100 grams of each reactant, we're asked to figure out what is the limiting reactant, what is the theoretical yield of water, and we want to determine the mass of excess reactant when the reaction has reached completion, okay? So in terms of our steps, let's try this time to use the ICE method. So first things first, we need a balanced equation. We need the moles of each reactant, and then we can enter the moles of each reactant into our ICE table. So let's start from here. So writing off from our word expression, let's pull up our word expression. So starting off from our word expression, for calcium hydroxide, would someone like to provide me the formula for calcium hydroxide? What is the formula for calcium hydroxide? Oops. Sorry about that. Yep, exactly right. So for calcium hydroxide, we have CaOH2. Would someone like to provide me the formula for hydrochloric acid? For hydrochloric acid, what's the formula for that? This is just for hydrochloric, HCl, exactly right. Okay, and then for calcium chloride, would someone like to volunteer with the formula for calcium chloride? Someone like to volunteer? Yep, CaCl2, exactly right. And as a byproduct, we generate water. Okay, now all we have to do is fill in our reaction coefficients. And on that note, my question to all of you is this equation balanced? Is this equation balanced as written? No. What element is not balanced? What element is not balanced? Chlorine. Yep, we have 2 chlorines on the right. We have 1 chlorine on the left. So what coefficient do we need? What times 1 would give us 2? What coefficient do we need? 2. Perfect. Okay. Now, taking a look, is there another element that is unbalanced in this equation? Is there another element that is unbalanced in this equation? Is there another element that is unbalanced in this equation? Or is this equation complete? Yep, water, exactly right. So water needs a reaction coefficient, and that is because we have 2 oxygens on the left and 1 oxygen on the right. So to balance our oxygen atoms, we need to adjust the coefficient of water. And what times 1 would give us 2 oxygens? What coefficient do we need to plug in? What coefficient do we need to plug in? 1 times what would give us 2? 2. Exactly right. Perfect. So now we have our balanced equation, and now we are given that we have 100 grams of calcium hydroxide, and we're also given that we have 100 grams of hydrochloric acid. This problem, to make things a little bit easier, I've given us the molar masses. So we know that in 1 mole of calcium hydroxide, we have a total of 74.09 grams. We also know that in 100 grams of hydrochloric acid, for every 1 mole of hydrochloric acid, we have 36.0 grams. Let me check. 36.46. So from that, we can calculate the moles of each of our reactant species. So let's complete that calculation at this time. So we've figured out that we have 1.35 moles of calcium hydroxide following sig fig rules, and we have 2.74 moles of HCl following sig fig rules. Okay, perfect. So we checked off our first 3 steps, and now all we have to do is format this information into an ICE table. So we have our calcium hydroxide reacting with hydrochloric acid to yield calcium chloride and water. We're going to now fill in our reaction coefficient. So we have a 2 in front of HCl and water, and we're going to fill in our initial moles. So initially, we have 1.35 moles of calcium hydroxide, and we have 2.74 moles of HCl. Does this make sense? Does everyone understand where we got these numbers from? Does everyone understand where we obtained our balanced equation from? Are there any questions at this point? Are there any questions at this point? Okay, now we're going to fill in our change coefficients. So what is the change coefficient for calcium hydroxide? What would the change coefficient be? Would it be minus 1x, 2x, 3x, 4x? Yep, it would just be minus x. Yep, exactly right, because our coefficient's 1. What would the change coefficient be for hydrochloric acid? What would the change coefficient be for hydrochloric acid? 2x, exactly right. Okay, we initially have 0 moles of our product, and we would expect our change coefficient for calcium chloride to be plus x and water to be plus 2x. Wonderful. So far, so good. Whoops, one moment. Okay, now what we're going to do is we're going to solve for x. So for calcium hydroxide, x is equal to 1.35 over 1, which is just 1.35. For hydrochloric acid, x is 2.74 over 2. Remember, we're dividing our moles by our reaction coefficient. And that in turn gives us a value of x of 1.371. So my question to all of you is, what reactant is limiting? What reactant is limiting in this case? What reactant has a smaller value of X? What reactant is limiting? Yep, exactly right. Calcium hydroxide is limiting. So we're going to plug in this value of 1.35 for X into each of the expressions. So minus 1.35 minus 2 times 1.35 plus 1.35 plus 2 times 1.35. Okay, so we have 0 moles of calcium hydroxide remaining. We have 0.04 moles of hydrochloric acid remaining, and we make 1.35 and 2.70 moles of calcium chloride and water respectively. So if we want to calculate the grams of water, all we have to do is take our 2.70 moles of water times 18 grams per mole of water. And that in turn gives us 48.6 grams of water. To complete this problem, if we wanted to calculate the grams of hydrochloric acid left over, all we have to do is take the moles of hydrochloric acid and multiply it by the molar mass, which is 36 grams per mole of hydrochloric acid. I guess we should be more specific, 36.46 grams. So let's punch that into our calculator really quickly. And in turn, we end up with 1.46 grams of HCl left, which we then simplify to 1.5 grams of HCl. So this is really the power of the ICE table, in that it allows you to efficiently calculate the final mass of products and reactants simultaneously. Are there any other questions on this example? Are there any other questions on this example that I can address at this time? We're at the end of our scheduled lecture period, so we'll pick up this lecture next class session on Thursday.